Hello student, I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I will continue from the last class. Last class I had discussed classification of crystalline solids. In that I have discussed molecular solids. In molecular solids I have discussed non-polar molecular solids, polar molecular solids, hydrogen bonded molecular solids, and in that also I have discussed ionic solids, metallic solids. Now I am going to discuss covalent or network solids. Covalent or network solids now I am going to discuss. A wide variety of crystalline solids of non-metals results from the formation of covalent bonds between adjacent atoms throughout the crystal. They are also called giant molecules, big molecules, GIANT, giant molecules. Covalent bonds are strong and directional in nature. Therefore, atoms are held very strongly at their positions. Such solids are very hard and brittle. They have extremely high melting points and may even decompose before melting. They are insulators and do not conduct electricity. Examples is silicon carbide, diamond and silicon carbides are typical examples of such solids. Graphite is soft and a conductor of electricity. This is the exceptional. I told you it is a non-conductor of electricity, but graphite is soft and a covalent conductor of electricity. It is a covalent compound, but it is a conductor of electricity. By a structure only you can understand. Its exceptional properties are due to typical structural its structure, due to this typical structure. Why it is a graphite is a conductor of electricity? Due to its typical structure. Carbon atoms are arranged in different layers. In case of graphite, carbon atoms are arranged in different layers and each atom is covalently bonded to three of the neighboring atoms. Three of the neighboring atoms in the same layer. The fourth valence electron, carbon, you know that 4 valence is there, then 3 is just attached to the neighboring carbon atoms. Carbon atoms are arranged in different layers and each atom is covalently bonded to 3 of its neighboring atoms in the same layer. The fourth valence electron of each atom, is present between different layers and is free to move, and it is free to move about. These free electrons make graphite a good conductor of electricity. Question is asked. The fourth valence electron of each atom is present between the different layers and is free to move about. These free electrons make graphite a good conductor of electricity. Different layers can slide one over the other. This makes a graphite a soft solid and a good solid lubricant. And here hybridization is sp2 hybridization, but in case of diamond it is a sp3 hybridization. Then this I have discussed about the covalent structure, covalent or network solids I have discussed. Now I want to just brief it different types of solids. All I have discussed, but now I want to brief it different type of solid with examples. Okay, because these are very very important and question is asked. Then first I will tell about the molecular solids. Molecular solids. Under the molecular solids, non-polar is there, second polar is there, third hydrogen bonded. There are three: non-polar, polar and hydrogen bonded. Then for this first I will tell, and then I will tell about the ionic solid, metallic solid and covalent or network solids. 4 are there total. Then first I will tell about the molecular solids. All things I have discussed, but I want to brief it. Then here constituent particles are molecules. Constituent particles are molecules in molecular solids. Constituent particles are molecules. And what type of bonding is there? This here dispersion or London forces will work. Here in molecular solids, which type of bondings are there, or attractive forces? Then here dispersion or London forces are active. And that is actually in molecular forces. This I told about the non-polar. In non-polar dispersion or London forces works. And in polar molecules solid, then here dipole interaction works. And in hydrogen bonded, then hydrogen bonding. In hydrogen bonded, hydrogen bonding. And what is the examples? Then examples of non-polar solid is argon, carbon tetrachloride, etc. And for this other example also you can understand: hydrogen, H2, I2, iodine, carbon dioxide. These I told you 5 are the examples of non-polar. Argon gas, carbon tetrachloride, argon gas that is in solid state, argon, carbon tetrachloride, H2, N2, CO2. And polar solid examples, then HCl, SO2. These are the polar solid. In solid state I am talking about, not the gas, because you are talking about the solid state. And hydrogen bonded example, then H2O, ice, what you are telling, ice, not vapor, not liquid. All we are discussing here about the solid state. They can exist in liquid also and gas also, but here we are talking in solid state. And what are the physical nature? Then all two, non-polar is soft, polar is also soft. Hydrogen bonded solid, that is hard. And what is actually, it's electrical you can say conductivity. Then all three are insulator. Means non-polar is also insulator, polar is also insulator, and hydrogen bonded solid is also insulator. Question is asked. And what about the melting point? Melting point, then for the non-polar it is very low, and for the polar low, and for hydrogen bonded solid low. Okay, only first one is very low. Now this I told about the molecular solids. Okay, means non-polar, polar, hydrogen bonded I discussed. Now ionic solids. Ionic solid, then its a constituent particle is ions. Name itself is ionic solid. They are solid, but its constituent particle is ions. And what type of forces are working? Then Coulombic or electrostatic forces. What are the example? Then example is sodium chloride, magnesium oxide, ZnS, zinc sulfide, also can tell zinc blend, calcium fluoride. Okay, this is the example of ionic solid. NaCl, MgO, ZnS, calcium fluoride. And it is hard but brittle. Its physical nature is it is hard but brittle. And this conductivity, what type of conductivity? Then it is insulators. Insulator in solid state, but conductors in molten state and in aqueous solution. This I discussed about the ionic solid. And what about the melting point? Melting point is very high melting point. Now I am going to tell about the metallic solid. Metallic solid, what is the particles, constituent particles? Then they have positive ions. Metallic particles have positive ions in a sea of delocalized electrons. In the middle, positive ion will be there, and surrounding delocalized electrons will be there. Means electrons can move. And what type of bonding will be here? Then metallic bonding. What is its example? Then ferrous, copper, silver, magnesium, etc. And what about the physical state? Physical nature, then this is a hard. Metallic solids are hard but malleable and ductile. What about the conductivity? Then it's obviously it is a metallic, it will conductors in solid state as well as in the molten state. In both state it is conductor. And what is its melting point? Fairly high. Ionic is only high melting point, but it is a fairly high. Okay. And last, that is the covalent or network solids. Then here what are the constituent particles? Then atoms. Here they will be atoms. And what type of bonding? Covalent bonding. What are example? Then silicon oxide, SiO2, quartz, what we are telling? Quartz, silicon oxide, SiO2. Another example is silicon carbide. Other examples, carbon, means diamond, in carbon also diamond. Next is aluminum nitride, ALN, aluminum nitride, and graphite. These are the examples of covalent solid or network solid. Silicon oxide, also you can tell quartz, silicon carbide, diamond, graphite, and aluminum nitride. Okay, in that silicon oxide is hard, very hard. Okay, physical state, you know that diamond is the hardest substance. Then all are hard, only graphite is soft. only graphite is soft. And what about the distance conductivity? Then all are insulator except graphite. Graphite is conductor. This is exception. And what is melting point? Very high, very high. It's look that metallic point will be very high, but it is only fairly high. But covalent or network solids, covalent compounds, particularly what I have told, all the things, silicon oxide, diamond, aluminum nitrides, a very high melting point. Even graphite also have very high melting point. Now I am going to discuss crystal lattice and unit cells. Crystal lattice and unit cell, very very important. Question is always asked. Okay, this chapter itself is very very important. Many questions every time they are asking in all examination, because this chapter comes under the tough chapter. Okay, and try to understand. You will feel very easy if you will understand. Otherwise, it will be difficult. Hence, here, when you are reading this chapter, studying this chapter, just you have to do too much imagination, because all structure, it is difficult to draw. By seeing the diagram, it is difficult to understand, because it is a three-dimensional structure. Generally, it will be three-dimensional structure. Then two-dimensional, you can understand very easily, length and breadth. Length and breadth, only in that two-dimensional you have to see. That two-dimensional you can understand. But third-dimensional, it is very difficult to understand by figure. Then how can you understand? Then you can understand, actually diagram will be there, but understanding will be difficult. Then how will you understand? Then very easy method is there to understand. Three-dimensional. What, how? And then simply you have to imagine that structure. As for example, cubic structure, it is difficult to make. You can make it on the paper, but you can't understand very clearly by seeing the this type of a structure. Tetragonal structure, hexagonal, it is difficult from the seeing the diagram. But if you will imagine that diagram, that just a cube, you have already know. Cube, length, breadth, height. This solid you have seen. Then taking this type of just imagination in a space, suppose it is standing in a space above the earth, like that you can understand. Then you know that cube, length, breadth, height, all are equal. Correct? Length, two length will be there, two height will be there, two breadth will be there. Then cube will be ready. Front all will be equal. Cube, total six length you will get. Total 6, all lengths are equal. Length, breadth, height. Total 6 side. Total 6 sides are there. Then just you can see 4 upside and 4 down. And just to join everywhere, you have seen already cubic structure. Then that just like that, see this, just to imagine that it is in a space. This figure, you think it is in a space. Then quickly you can understand all side, how many sides will be there. Then total one, up one side, down one side. Correct? Left one side, right one side. or direction wise better you understand. Upside one, down one, 2 layer is over, and north and south, east and west, total 6 face. Up and down, 2 face, north and south, 2 face, east and west, 2 face, total 6 faces. Correct? In this chapter, without understanding these things, imagination, it is very difficult, I am telling you. Even you will, picture is made in front of you, it is difficult to understand. You can draw the figure, but by seeing the diagram, it is difficult. Okay, and so what I am telling you, that you have to imagine in a space, then easily you can understand all. You can say this this chapter, what so many diagrams are required, many structures are there, complicated structures are there, then you can't understand simply by seeing the diagram. But it is very easy, I am telling you, very easy if you will imagine in a space, then all things you can understand. Then now I want to brief you before going to the specific, means liquid lattice, this crystal lattice and unit cell. Only here I want to brief it, all important things, so that you can understand easily, or better you can understand. Then here what are the 2-3 points only you have to understand, then this chapter will be very easy. What are that things? Then first you think that different type of structure may be there. Different type of structure, you have to know what are the different type of structure. Correct? As for example, that these things, one may be primitive and centered, you can say cell, primitive and centered unit cell. And the structure I am telling, this is the you can say cell, but I am telling about the different structure. Okay, different structure. First you have to remember. Remember means you first you should know the name of the different structure. Correct? Because some structure will be similar. Some structure will be similar, but not the same. Then first you understand the name of a different structure. After that you can understand what are the differences. Even similarity is there. They are similar, not the same. Then I will tell you some name of the structure. And in that you will find some similarity. That is a different case. I will tell condition also. But now I am telling the different name of the structure. Then just like a cube, one structure is cube, that is called cubic structure. Second structure is tetragonal. Tetra means 4. Tetragonal. And third structure is orthorhombic. Fourth structure is hexagonal. Hexa means 6. And fifth structure is rhomohedral. RHOMBO. RHOMBO. Rhombohedral. Next, sixth structure is monoclinic. And seventh structure is triclinic. Then this structure, you should know the name of different structure. These are the name of different structure. That now we will find by seeing, even I will try to send some structures. This structure I will try to send. But here you will find that all structures are made from the same side. All structures are made from just like a cube only. 6 side. All only some hexagonal you will find different. Hexagonal you will find there also you will find these things 6 only, 6 side also there you will find in even hexagonal also. Okay. Then here you are just like a cube, 6 sides are there. Here also you will find 6 sides. Appearance will be also looking by that it looks like same, but all are different. Then how you will differentiate? How will you differentiate that technique I am telling you? Okay, you will understand very easy. It is actually very tough. It's a very tough chapter, very tough. By diagram is there, and 3-dimensional diagram it is very difficult to understand by seeing the diagram. But what I am telling you, if you will follow these things, what I will tell you now, one thing I told you, imagination. Or directly you could just, in real practice, if you will see in any lab that type of structure, then you can understand very easily. Okay, but all structure you will not get. Then better what I am telling you, that thing you follow. Then first I told you, do imagination. And after that you have to think when sides are same number, then how they are differing, where they are differing. This is important things. Then here 2 things you have to consider. 2 things. First things, that angle. First you say these things, sides, same sides are there, 6 sides are there. Then there are 2 differences. First, that always they will be not 90 degree. In cube you have seen all angles are 90 degree. Just like a room you see, every corner is a 90 degree. Every corner. This is also just like a cube only, a room where you are living. Correct? Suppose 10 into 10 rooms are there. Then you will see that every side 10s are there. It is just like a cube. Angle is 90 degree. But now, just always it is not necessary that all sides will be equal. Rectangle you have seen, length and breadth only differing. In rectangle, that length is different, breadth is different. Correct? Height is also different. Then these things you have to consider, that length may not be equal. Length may differ. Or length, breadth, height may differ. Okay. And this is the first important thing, that all length always will be not equal. In all structure, length always will be not equal. Okay. And second important things, angles also will be not always 90 degree. It may differ. Correct? Then length and angles always will vary in different structure. That's why now you can understand that many possibilities are there. Many possibilities are there for the structure. Correct? Because always length will change and angle will also change. Then when length will change, angle will change. Then different structure will be there. Even number of sides will be the same, but structure will be different. Then in 7 structure, what I told you, same thing is there. Sometimes what will happen, that only in one structure, that 2 sides will be same, third will be not the same. Angle will be maybe 2 sides angle will be equal, other sides angle will be different. Correct? Then now you can understand that if angles will differ, suppose two sides are same, third is not, or rest are other sides are not the same. Angles are two angles are same, others are differing. Then see, they can make possibilities for many structure. Then these things you have to consider. Okay. After that, if you will think like this, then that length may be different, angle may be different, then the structure may be different. And the length will be different, angle will be different. Then structure will be different. Then that I will tell you that in these 7 structures, what will be the sides, how many sides are equal or not equal, and what are the angles. Then all seven what I told you, cubic, trigonal, orthorhombic, hexagonal, rhombohedral, monoclinic, triclinic. In all you can say structure, sides, condition of sides and angles are different. Okay, I will tell, and I will tell the examples also. Okay, actually here what is happening, that in solid state, that you know that all things are made from the atoms, all solids, either solid, liquid, gas. Then gas, you know that gaseous molecules are free to move, they can make any shape. Correct? Gaseous molecules, where will you keep, that shape it will make, because that is not fixed. And liquid also same way, they are also moving. Gaseous molecules are very far from each other. Liquids are little close. That's why they can say you can see it, because they are little close. Correct? But they can move. That also where you will keep that shape and volume it will take, just like air. If you will keep in a bucket, it will take bucket shape. If you will keep in any other you can say utensil, it will take that utensil, that shape of utensils. Then both are moving. Shape is not fixed. Shape depends upon the where they are keeping. If gas you will keep in a cylinder, then cylindrical shape. Correct? Liquid you are keeping in a cylindrical shape, or anywhere. But solid has a fixed shape and volume. Fixed shape, bricks, you have seen bricks. Its shape is fixed, volume is also fixed. Correct? Then because it is fixed, it is fixed because their atoms from which it is made, they are arranged in a proper way. In solid, in any solid, if you will see by microscope or electron microscope, then you can see that how all atoms or ions or molecules, any solid can say formed due to this. In that solid already discussed, it is formed by atom or ions or molecules at any corner. It is arranged. Many molecules are arranged in a proper way, or atoms or ions are arranged in a proper way. Then these atoms in any solid, it is arranged in a proper way. That is called a crystal. Okay, in chemistry you will tell, as for example, sodium chloride, NaCl, salt. If you will see the salt structure by microscope, NaCl, then you will find very clearly, you will see how all Na and Cl are arranged. NaCl, again Na, again Cl, again Na, again Cl. It is arranged. Then here, like that way, KCl is also there. Sodium sulfate, Na2SO4. 2Na, again SO4 will be there. Or SO4 ion will be in the middle, one side Na, other side Na plus, Na2SO4. Like that way, any other solid, K2SO4, same way, SO4 may be in the middle, SO4 2 minus, sulfate ion, and potassium plus, K plus, just neighboring will be there. Then any solid, aluminum sulfate, Al2SO4 potassium aluminum sulfate. All structure you will see different type of molecules are there. No, you know that substances are crystals are of different side. KOH, NOH, correct? Then if you will see, you will find they are arranged in a proper way. And here again one more things I want to tell you. Just like in polymerization you have seen, polymer, they will polymerize, means repetition will be there of the same structure. You have seen that ethylene, many ethylene molecule will repeat. CH2, ethylene, double bond you are telling, then CH, CC double bond, again CC double bond, again CC double bond. Like that way repetition will be there. And other thing balancing will be filled by hydrogen, that you know. Then polyethylene, poly means many, more than two. Ethylene means repetition is there, ethylene. Acetyl, polyacetylene, then acetylene, they will, we can say, polymerize. Then like that way, here you will find, if size is big, crystal size is big, then what you will find? That suppose NaCl is there, then 2 ion you are talking about, Na plus Cl minus. Then every time NaCl will repeat in a proper way, you will see that NaCl completely it is repeating. Then it will become big size. Then why will you study full big size? Then a smallest size which is repeating, that is called unit, 1 unit. In big size, many units may be there, many units. Then 1 unit means, because this unit will repeat. Okay. Then NaCl, as for example, NaCl. Then a smallest, you can say structure, or size, whatever you can tell, which will repeat always. That structure will repeat always. That is called actually unit cell. Unit means 1. And that will repeat, and it can make a big size. Then a smallest size, or repeating unit. That's why unit we are telling, because that molecule only will repeat every time. Then that is called unit cell. Okay, unit cell. Then now actually I have discussed, briefed you about the these things, about the structure, because that now you can understand easily. Correct? And one more things here, angles I am telling you. Angles, just like in room only you can see how many, any corner you consider, any corner, how many angles will be there. Then just to think, in any corner in your home, house, room, any one corner you consider, how many angles are there? Then only 3 different angles you will find. 3 angles, not different may not be. Then first you will see the height, then one side length, other side breadth, and upside height. Then suppose length you consider as a small a, and breadth you consider as a b, a small b, and height you consider as a c. Correct? Then A, B, C. 3 sides are there, A, B, and C is height. Then now angle between A and C, one angle, means length and height, between length and height, one angle. And second angle B and C, means breadth and height, two angles. And third angles A and B, length and breadth, three angles are there. Correct? Height and length, one angle, between height and length, alpha you can tell. And other angle, that breadth and height, beta you can tell. And length and breadth angle, that you can tell alpha, beta, gamma you can tell, gamma angle, alpha angle, beta, gamma angle, three angles. This is very, very important concept. Quickly you can understand. By diagram it will look very complicated. Okay. Then now I told you, always angles means in that way angle you have to consider. Every corner, three angles will be there. Every corner. And it is not necessary that always in room you are seeing 90 degrees there. All angles are 90 degree, just like a cubic. But it is not these things. If you will make a change in angle, then the structure will change. Suppose one side 90 degree, other side 30 degree. Third side again some other angle, this angle. Then see what type of a structure will be there. Correct? It will look like leaning like that will be there. Angles are leaning. Just like a tent house you are making, any angle you can make. Cubic also you can make, triangular or this, so many you can shape you can make. That depends upon the angles. Then now I am going in details. Okay. Then now I will discuss about the first these things, crystal lattice and unit cell. I was discussing, I have briefed you about the chapters, and that is the very not very brief I discussed you. This will help you understanding this chapter. Then now I am going in details. The main characteristics of crystalline solid is a regular and repeating pattern of constituent particles. If the three-dimensional arrangement of constituent particles in a crystal is represented by a diagrammatically, in which each particle is depicted as a point. Particle you can tell as a point. One point means one particle. In which each particle is depicted as a point. The arrangement is called crystal lattice. This arrangement is called crystal lattice. Thus, a regular three-dimensional length, breadth, height, always in a space, you understand. Thus, a regular three-dimensional arrangement of points in a space is called crystal lattice. Question is asked, what is the crystal lattice? Then you can answer like that. A regular three-dimensional arrangement of points in a space is called crystal structure. Okay. I will try to send the diagram also. Then suppose big size is there. Cube, suppose you have taken little big cube, just you think cube. Then you can cut it in so many pieces. This cube you can cut it in so many pieces. Okay. Then after that it will become very, very, very small. You will find a big cube was there, and you have cut it in many pieces. Correct? Then all pieces will be equal finally. Okay. Then After that, you will not able to cut. It become very small. As for example, cube you have taken, one you cut it from the middle, correct? Again you cut from again the middle. Always you cut from the middle. Then finally you will get a cube only, but a very small cube. Further you can't cut it. Then in diagram it is made like that. Just diagram will be made like that way, that it is made. You will feel that it is made from so many cube. Length, breadth, height is equal in all cube. Even for small you cut, that length, breadth, all height will be equal. Then you can, in a diagram, you can show like that by making picture also, that a smallest whatever is size what you will get, a diagram, smallest, then that is like a 1 unit, and that is called actually cell unit, okay, or unit cell, because that you will repeat, it will become bigger size, okay. Then this I have told you. There are, this I told about the crystal lattice, okay, arrangement, a regular 3-dimensional arrangement of points in a space is called a crystal lattice. A portion of crystal lattice, that is a smallest portion, that is called actually unit cell. There are only 14 possible 3-dimensional structure lattice. Again important point, question is asked, how many? Then there are only 14 possible 3-dimensional lattice. Only 14. This is actually one scientist was there, mathematician. His name was Bravais. His name was Bravais, Bravais, Bravais. Then due to this mathematician, actually just he has told this thing, that possibilities, there are only 14 possibilities, 14 possibilities, 14 possible 3-dimensional lattice, 14 possible 3-dimensional lattice, and these are called, on his name it is called Bravais lattices. Bravais lattices, Lattices, 14. That is this 14 possible 3-dimensional structure is called Bravais lattices. After the French mathematician, there was French mathematician who first described them. And this, what are the characteristics? What are the characteristics of this crystal lattice? Then the three main characteristics are there. Three main characteristics of lattice. Okay, characteristics of crystal lattice. Then what are that 3 characteristics? Then first, each point in a lattice, each point means, lattice means you have to understand that some structure, crystal you can understand, some fixed structure. Lattice means fixed structure. In that atoms are arranged, then atom is a point charge, that you know. Then 3 characteristics are there for the lattice. Then first is that each point in a lattice is called a lattice point or lattice site. Correct? Each point means atom, we are talking about the atom, molecule, ions, whatever we. Each point in a lattice is called lattice point or lattice site. Okay, because the structure is made from the atoms. Then each atom, I am talking about, each atom or each point you can tell in a lattice is called lattice point or lattice site. Second, each point in a crystal lattice represents one constituent particles. That point is called particles, constituent particles. Each point in a crystal lattice represents one constituent particles, which may be an atom, a molecule, or you can tell molecule, group of atoms. Molecules means group of atoms, or an ion. These points may be atom, may be molecule. Molecule means group of atoms, or ion. Third characteristics, lattice points are joined. All points are joined. Lattice points are joined by straight lines. A straight line just to join, because they are in a point, just to join with a straight line. Then lattice points are joined by straight lines to bring out the geometry of the lattice. If you will, every crystal has different structure. How will you come to know the what type of structure is there? Then if you will join all atoms by a line, a straight line, then you will find, oh, this type of shape is there. Okay. Then these three characteristics I have told you about the lattice characteristics. And now unit cell. Come to the unit cell. Already I have told you. Again I am telling you. Unit cell is the smallest portion. Correct? Unit cell is the smallest portion of a crystal lattice, which when repeated in different direction generates the entire lattice. Correct? In all direction. Then question is also asked, what is the unit cell? Then unit cell is the smallest portion of a crystal lattice, which when repeated in different direction generates the entire lattice. Okay. And what is the characteristics of unit cell? What is the characteristics? Then I am telling you characteristics. Two characteristics are there. First, the dimension along the three edge A, B and C, small a, small b and small c. How it is represented, that I am telling you. Its dimension along the three edges, E, D, G, E, S, edge, axis, what you are telling, edge, E, D, G, E, S, edge, A, B and C, small a, small b and small c. These are their edges. Three edges are, what are the edges? E, D, G, E, S, edge. Then it is represented always by a small b and a small c. These edges may or may not be mutually perpendicular. May or may not be, means 90 degree. This is the first thing. Already I briefed you. Second things, angles between the edges. Angle I told you, alpha, beta, you can tell. Alpha angle means, alpha angle if you are talking, that it means between B and C, edge B and edge C, between that angle is called alpha. Beta angle between A and C, edge A and edge C and C. And gamma then between A and B. Already I discussed by giving example. Thus a unit cell is characterized by 6 parameters, 3 edges and 3 angles, 3 plus 3, 6. Then this I told you that it is characterized by 6 parameters, a small a, a small b, a small c, and angles, 3 angles, alpha, beta and gamma. These parameters of a typical unit cells, that by seeing the diagram, simple cube structure, I already told you that I can understand. Or a room. In a room, all angles I already told you. You can understand very clearly. Now I am going to tell about the primitive and centered unit cell. These are the actually basic things I am telling you. After that, because these terms will be repeated many times, then you understand it. Primitive and centered unit cells. Unit cells can be broadly divided into two categories. Unit cell you can divide in two categories, broadly divided into two categories. First, primitive, and second, centered unit cell. Centered unit cells. Then now, what is the primitive, what are the differences, now you understand for both. Just you listen carefully, because when you will understand concept, then it will be very easy entire chapter. Okay, and so you try to listen carefully. Then what is the primitive unit cell? What type of for what type of cell you will tell primitive? Then when constituent particles are present only on the corner positions of a unit cell, it is called a primitive unit cell. Again I am telling you, when constituent particles, maybe atom, maybe ion, maybe atom, molecule, ion, anything. When constituent particles are present only on the corner position of a unit cell, it is called primitive unit cell. Example, as for suppose you cube you have taken. Now imagine cube is hollow. Only a structure, you just think. Six corners are there. No, 4 corners upside, 4 corners down. Sides are 6. But corner, just cube corner you count. 4 corner upside, 4 corner down. Total 8 corner. Then if atoms are only found at the corner, all corner, not in the middle and side, only on the corner, if atoms are there, only on the corners, means 8 corner, 8 atoms, or 8 ions, or 8 molecules. Then that type of a structure, that type of cell is called a primitive unit cell, only at the corners. When constituent particles are present only on the corner position of a unit cell, it is called as a primitive unit cell, and only this cell will repeat in all direction. Then you will get big size. Okay, then now always here while studying you think only unit cell. Okay, this is the I told about the unit cell. This I told about the primitive unit cell I told you. Now what is the centered unit cell? Centered, name itself is a center. Centered unit cell. Then here condition is there. 3 conditions are there. Okay, your question is asked. Hence, and try to understand. 3 conditions are there. First, I am telling. First, I try to understand what is the centered unit cell. Then, same things are there. Condition is different. When a unit cell contains one or more constituent particles present at positions other than corners, in addition to those at corners, it is called a centered unit cell. Again, I am telling you, when a unit cell contains one or more constituent particles present at positions other than corners, in addition to these at corners, it is called a centered unit cell. Means, example I am telling you, just to think, you cube you only you think cube, and you think that now cube back ends are empties are there, only corner and other things, just like you can think it is a transparent cube, you can see every direction, you consider like that. Then now here's centered cube unit cell means here first all corners it will be there, at all corner atoms will be there. Other than this, in addition to this, if some particles are also present, these are there, 8 corners means 8 particles are there, this should be there. But in addition to this, other than this, if some particles are also present, then this is called actually centered unit cell. Okay, I told you that other than corners, in addition to these, it is called a centered unit cell. Correct? Then this is the only condition when a unit cell contains one or more constituent particles present at positions other than corners, because corners already it is occupied. Hence, other than corners, any other place it is there. Already corners are there, that will be there. Other than that corners, if some you can say particles are also there somewhere, then it is called centered unit cell. When a unit cell contains one or more constituent particles present at positions other than corners, in addition to these at corners, okay, then it is called a centered unit cell. Then now 3 conditions are there. Where there will be these particles, where will be there? Then three possibilities there. 3 possibilities. First possibility is that body-centered unit cell. Body-centered, name itself is there. Body-centered unit cell means if you can say 8 corners are covered, unit cell this is there, cubic, 8 corner, 8 particles are there. Now suppose one more is there, 9th, then that is if it will be at the center of the cube, in the middle, body centered. What are you telling? Body center means such unit cell contains one constituent particles, maybe atom, molecule or ion, at the body center, in the middle, at the body center, besides the ones that are at corners. At corners is there, but extra 9th one is there, that is in the middle, it is in the body, middle of the body, center point it is there, and that cube is there. And see that in the cube from every side equal distance, in the middle in the middle this is there, one particle is there. Then you will think how one particle will be in the middle simply arranged. Then that is arranged due to the forces, due to the attractive forces. It can arrange in the middle only. From the all 6 sides are there in a cube, 6 sides are there. Then that molecule will be equal distance from each side in the middle. Okay, then that is called body-centered unit cell. One cell will be like this only, that atom may be in the center, body center. That's why name itself is given body-centered unit cell. Now second, extra atoms may, where other places can be, what are the possibilities? Then that is called face-centered unit cell. Second condition, all are body-centered, but only conditions are different. face-centered unit cell. Here, such a unit cell contains one constituent particles present at the center of each face beside the ones that are at the corners. Means cubic lattice, you take always example that easily will understand. Then 8 are there, and now suppose extra atoms are 6 faces are there. Then now up face you consider. Up face in the middle, in the center of the first face, up face, one particle is there. Other particles may be on the other middle of the other face. 6 faces, then 6 particles may be there at the center of each face, not body. Already that is one condition. Second condition, that in the middle and the center of the each face, one particle may be there. Okay, that's why its name has been given face-centered unit cell. Such a unit cell contains one constituent particles present at the center of each face, besides the ones that are at the corners. Means corners are there, that will be fixed. And extra things I told that extra particles may be arranged, you can say, at the sides, at the middle of the each face, at the center of the each face. Okay, that's why it is called as a face-centered unit cell. Okay, and third I told you, third example is end-centered, end-centered unit cell. Then now end. Then meaning of end you understand. First end, second end. First end, second end. Now 6 faces are there. Suppose north and south. Then if can say 2 particles are there, other than corners are there, forget it. Corners suppose already occupied. Then suppose 2 are there, 2 particles are there, north and south. One is near the north, not at the face. Correct? Far from the face. Both are far from the face. Correct? But near the end. Then like that way, north, south I told you, east, west also may be there. Up and down also may be there, same condition. Then that is the situation of end-centered unit cell. That is called end-centered unit cell. In such a unit cell, one constituent particles is present at the centers of any two opposite faces. Correct? In this case, that in such a unit cell, one constituent particles is present at the center of any 2 opposite faces besides the ones present at its corners. Correct? All corners are occupied. Then this you can say both faces, opposite faces near the face, middle, center you can tell, but not at the face. Correct? Near the face, opposite faces. Okay, and near the center. If you can say atoms are present or particles are present, end, then that is called end-centered unit cell. Again I am telling you that in such a unit cell, one constituent particles is present at the center of any 2 opposite faces opposite faces, correct, beside the ones present at centers. This I told about this centered. Two things I have discussed now here. That first I have discussed, that is the primitive unit cell, and second I discussed centered unit cell. In three cases I have discussed, and already I have told you in all there are 7 types of primitive unit cell. How many types are there for primitive unit cell? Primitive, give importance for the primitive word, primitive. Then there are 7 types of primitive unit cell. Then here primitive unit cell means, here you understand, whatever be a structure, all corners, at all corners particles are there, only at corners. Means if all corners particles are occupied in any structure, is then that is called primitive unit cell, because all corner particles are occupied, whatever with the structure, all 7 structures are there, and all structure corner position particles are occupied. Then structures are different, 7 structure already told the name. Then all are called primitive unit cell. Then there are 7 types. First type already told you, cubic. Second, tetragonal. Third, orthorhombic. Fourth, hexagonal. Fifth, rhombohedral. And 6, monoclinic, and 7, triclinic. All are example, because all corners are occupied by, you can say, particles. Then 7 structures are there, but all are called primitive unit cell. Okay, and here again I am telling you very important things, that crystal, what you will find a crystal, then it is not necessary that only at the corners, particle will be found. Only in the one structure you will find that a corner is already occupied. What I told you, the other 3 cases, that also may be present. Then because every corner particles are arranged, hence all structures are, I can say, primitive unit cell, and other will be also name will be given, but that will also come under the primitive only. Even on the each side, each face, or in body center, face center, and on, that also will be there, and that also will be there. Then primitive means that every corner it must be there, particles must be there. Then now I will tell some these things, but time will be more. Okay, because it will take a little more time. Today I am stopping only here. Next class I will tell the condition examples, because it will take more time. Then in a hurry I can't discuss. Then this 7 primitive unit cells and their possible variations as unit cells I will discuss next class. Thank you.